feel extremely delighted to meet viewers of my channel in yet another module, that is Success to Gate Control Systems Module 3. Here again I am going to cover the root locus problems that appeared in various gate examination question papers. Let me move straight away into the question 1. The question 1 is taken from GATE 2017 Electronics Engineering Set 1. Question number 47. A linear time invariant system, LTI system with a transfer function, is connected in the unity feedback configuration as shown in figure. So it's a normal closed loop system. H of s is equal to 1. For the closed loop system shown, the root locus for 0 less than k less than infinity intersects the imaginary axis for k equal to 1.5. The closed loop system is stable for, so we have to choose the correct option among the 4 options. Since we have to see where it intersects the imaginary axis and the closed loop system stable, anyway, where it intersects they have already given, so we have to check the stability. We have to use the route stability criterion only. So the open loop transfer function is given. So the characteristic equation is 1 plus g of s h of s equal to 0 as usual. So g of s we have straight away written, h of s is 1. So we have to take LCM and simplify. And if we arrange properly the terms, 1 plus k into s square plus 2k minus 3 into s plus 2k plus 2 equal to 0. So a characteristic equation we get. This characteristic equation we have to formulate the route array. So s square coefficient we have to write first. This we have to leave. Then this coefficient we have to leave. We have to write. Then this coefficient we have to write in the next row. So this into this minus this into this divided by this. This is 0 of course. So this into this minus 0 divided by this is 2k plus 2. So always last element in the route array will be the last constant coefficient of the characteristic equation. So for the system to be stable, all the first column elements are to be positive. Anyway, this will be positive when k is greater than minus 1. This will be positive when k is greater than minus 2. And this will be positive when this 2k is greater than 3, that is k is greater than 1.5. So when k is greater than 1.5, this is also positive, this is also positive, this is also positive. Therefore, k greater than 1.5 is the correct option for closed loop system to be stable. Of course, this intersects imaginary axis, that those things and all we need not bother, because our aim is to not to determine the frequency of sustained oscillations or something like that. Because when k equal to 1.5, this becomes row of zeros, then we have to form auxiliary equation, all that. So that is not at all required for us. The question is stability range, that's all. So k greater than 1.5, option A is correct. So let us move to the second problem. So the gain at the breakaway point of the root locus of a unity feedback system with open loop transfer function g of s h of s equal to ks by s minus 1 into s minus 4 is, so 4 options given. So we have to choose the best option. So it contains 1, 0 and 2 poles. So 0 at origin, poles at plus 1 and plus 4. In order to have a feel of the problem, I have just drawn the root locus segments on the real axis. So we know very well that any point between 1 and 4, if we take, to the right hand side there is one pole, therefore it is odd, therefore this is a root locus segment, therefore root locus starts from here, similarly a root locus starts from here, definitely they will break away, therefore breakaway point will be here between 1 and 4. And we know very well that this cannot be root locus segment, because the right hand side of this 2, that means even. Here this should be a root locus segment, because to the right hand side 1, 2, 3 odd. So here also we may get a break in point, maybe breakaway here, and one both the root loci go like this, one terminating on 0, one terminating on infinity, something like that we may get. So we have to check that. Anyway, that break in point is not at all required, because the question is breakaway point only. So 1 plus characteristic equation we have to write as usual. Breakaway points are the solutions of dk by d is equal to 0. This we know very well from our root locus, that is control system lecture series lecture 10. So characteristic equation we know. So k we can write. So differentiate this k with respect to s. So if we simplify by u by v rule, that is v du minus u dv by v square, we get s square minus 4 equal to 0. So we will get s is equal to plus 2 minus 2. Plus 2 is a breakaway point because 2 lying between these two and it lies on root locus. So if we find out k, so minus of s minus 1. So 2 minus 1, 2 minus 4 divided by 2. 2 minus 1, 1. 2 minus 4, minus 2. So minus, so finally it is going to be 1. So gain is 1. So gain at the breakaway point is 1 and it is matching with this. Therefore option A is correct. Let us move to the third problem. So it is taken from Electronics Engineering Set 3, question number 48, GATE 2016. So the forward part transfer function and the feedback part transfer function of a single loop negative feedback control system are given as. That means a normal closed loop system, they have given single loop negative feedback control system. That's all. So G of S, H of S. That means it's simply unity feedback system. That's all. If the variable parameter K is real positive, then the location of breakaway point on the root locus diagram of the system is dash. So it is again a problem on breakaway point. So breakaway points are solutions of dk by ds equal to 0. So write the characteristic equation. So 1 plus g of s into h of s equal to 0. That is what I have written. Therefore k, when we simplify, this will go this side. So finally minus of s square plus 2s plus 2 by s plus 2. So use u by v rule, that is v du minus u dv by v square. We will get dk by ds as s square plus 4s plus 2 equal to 0 after simplification. So if you solve this, we will get two roots. One root is minus 3.4 and 4. That minus 3.4 and 4 is definitely on the root locus. That is why I have drawn this. Here again I have drawn this very simple. S square plus 2s plus 2, two complex poles. So minus 2, 0. Therefore root locus segment on the real axis will be something here. Of course root locus will start from here and start from here. They will break away. One will terminate at minus 2. Another will terminate at infinity. All that we know. That's not the question. Breakaway point where it occurs, that's all. So breakaway point, definitely it should be a point on the root locus. This cannot be a point on the root locus. This cannot be a point on the root locus because here root locus segment is not there. That rule is not satisfied. Root locus segments on real axis. Therefore minus 3.4 and 4, since it is to the left of this, definitely it is on the root locus because there is only 1 0 to the right of this. Right. So let us move to the next problem. So it is taken from Electronics Engineering Set 1, question number 45, GATE 2017. Open loop transfer function they have given s square plus 5s plus 5. The value of k at the breakaway point of feedback control system's root locus plot is dash. So it is numerical answer type question. So as usual, breakaway points are the solutions of dk by ds equal to 0. So write the characteristic equation. From the characteristic equation, write the expression for k. Write the expression for dk by ds. So we get 2s plus 5 if we differentiate. So if we solve, s is equal to minus 2.5. So to have a feel of the problem, s square plus 5s plus 5, if we find out the roots, one root will be minus 1.38, another root is minus 3.62. Therefore root locus, one root locus starts from here, another root locus starts from here. Of course they have to travel in the opposite direction. Of course after breaking away they will move to infinity. Anyway, how they move to infinity, all that we are not bothered. Those rules and all we are not finding out. Is the breakaway point in between these two? That is what we are supposed to check. Yes, we got minus 2.5. It is between these two. The question is not the breakaway point, the value of k. Therefore, k we have to substitute in this expression. Substitute s as minus 2.5. We get k is equal to 1.25. So we can see in all these four problems, we have used the same simple standard approach which I have already used in the previous module as well as control systems lecture series lecture 10. So no new formula, new expression, new concepts are used just for the sake of coaching the GATE examination solution. So if you know the basic concepts very well, solving GATE examination question paper is nothing. So that impression only I have created so far in all my GATE modules. I am sure you would have understood the approach. If you have any doubts, any queries, you can post the queries or feedback to this mail ID. You can also WhatsApp to this number. To have a more detailed approach on root locus technique, you can refer control system lecture series lecture 10 in my YouTube channel. This is the URL of the video. So I need more support from you in terms of watching the videos, sharing the videos, and subscribing my channel. I am sure you will do that. So thank you very much for your patient watching my video. So I will meet you in the next module, module 14, wherein I will be dealing with GATE examination question papers pertaining to frequency response analysis. Thank you.